second slide. Back. Are we good? Okay. What?
I think they need the lights for...
Okay, fine. Okay, we decided to do a project in static equilibrium, and we built this arm that you can see over here. Slide, please. Okay, and this, you can read this. This is basically what we wanted to demonstrate concepts of physics, mechanical engineering, usual stuff. Okay, and this is...
Okay.
Find this one.
All right, this project really pertains to what's called static equilibrium, which means that the object is not moving. And when an object is in equilibrium, the summation of all the forces and all the torques acting on it have to add up to 0. And that's basically what we're going to be demonstrating here. Okay, next slide. All right, in doing this project here, we used, hey Paul, maybe you want to point to them as we go through. We used 2 servo motors.
Okay, there's one on the bar, the beam that controls the weight that moves it forward and back, and one that controls the angle, sort of a winch mechanism.
Okay. We used a rotary potentiometer to measure the boom angle.
Link through the pivot here, and that measured, as you said.
And we used 1 slide potentiometer.
And that was across here.
And we used something that was a little novel at the time. We used a load cell supplied by Parallax.
And that's over here, and it measures the amount of compression.
And you can, why don't you point to it right there on the mechanism?
It's right here hanging off the side.
It's a compression. It's basically a strain gauge. This one happens to be a compression cell, not a tension cell, which caused problems. Okay, and we're using a lead screw here to drive it back and forth.
That moves the weight.
Okay, next. All right, here's a picture of the electronics board here. We're using 2 ACD chips. We're sensing the voltage at both potentiometers, and these chips are being used to convert the voltage reading to an angular or position measurement. And on the breadboard, we have a couple of capacitors, resistors, and the most expensive piece of electronics we're using here is the basic stamp chip. And of course, all right. And here's this.
2 ADCs. Both of them are sending a thing to the motors, which is very, very similar. One of them has a 0 offset on the rotary, so that we're trying to do away with the dead zone. We didn't need a span adjustment. The other one doesn't have that because it was linear and it was perfect. This was the flexi force. This is a strain gauge, and this is the way it had to be wired in.
That was the way they recommended
recommended using a typical RC circuit.
And looking back, maybe we could use an A to D chip instead, but this is what we used. Next. Okay. All right. Typical operation. This is the way the thing operates. The operator at the computer will select a boom angle, which is angle theta here.
That would control the length of the boom.
Okay, and you can select any degree you want from 5 to 55 degrees. Then it will come back and ask you for a position for the slide weight. And as you can see here, one of our calibrated weights there, the fishing anchor, will move to a new position. Okay, and for feedback, we're sensing a boom angle, which will appear on the screen and show you that you did get to the desired angle you wanted to. You would also, the second part will show you that you achieved the correct position. And we're sensing cable tension with the load cell. Okay, and we're doing a series of calculations, which I think appear in the following slides here. Go ahead. All right, so basically here, what we're doing here, we're taking a summation of torque about the pivot point, and we're calculating the forces in the x and y direction. And what we're doing here, we're actually calculating this angle based on the tension that we're recording, and we're also calculating the reaction forces at the pin there. Okay.
Basically, the same kind of setup is on bones in the human body. If you think of your forearm elbow joint, it's exactly the same thing with the same forces working on it. Knee joints, cranes, cantilevered bridges, backhoes, all use basically the same kind of setup.
I just want to add something to that. This is a typical problem students in an AP physics class would be doing. And this problem, as Paul said, has a real-world applications in these 5 areas that we pointed out here. And there's probably others that we didn't think of.
Yes. And we'd like to thank some people also, so if you did it slowly. Nathan, thank you. Yvonne. Sal. Hung. Imran. Okay. And the NSF, of course. And, of course, Professor Capilla.
Okay. And now we're just going to run through a demonstration here. So, Saul, if you would.
Okay. Get the code running. Okay, run that code. It's interesting because we kept running out of variable space. We filled the EEPROM. We had to cut variables over and over again.
Right, so here it's coming. It's asking for a boom angle.
Boom angle between 5 and 55.
What do you suggest?
We're not suggesting anything.
Anywhere between 5 and 55.
What did he pick?
50.
Ah, we're going all the way up, huh?
Okay.
Yeah.
And now it's moving up to 50 degrees. We actually have a guideline on the back.
So you can't see it. It's a transparent protractor.
Okay, it's now at 20 degrees.
And if you look right here, it's telling you what angle you're at.
It's now close to 30.
There you go. We're at 30.
Now very, very close to 40.
And as you see,
50 degrees.
and we stopped at 49 degrees because we have a 1 degree accuracy here, plus or minus.
Now
And
it's
now-
asking for a boom angle between 17 and 22.
Maybe-
Right now it's on 19 centimeters from
Go
the
ahead.
pivot point.
Pick a whole number.
So it's moving forward to move this 4-ounce weight to 20.
And then you got to watch, because what's going to happen here, all the calculations will appear on the screen, and this thing will do something.
Okay.
It goes back to its initial starting position, and here we display the cable tension in units of ounces, newtons,
The
and
initial conditions, and it calculates the horizontal force, the vertical force, which of course is downward, and it tells you the angle of the horizontal
and the cable angle.
and the cable angle.
And that's it.
Sorry.